Hey everyone, let's take a look at the first two problems in section 2.5 and Achieve. In each of these, we're going to evaluate the limit if it exists. And this is our first one right here. First thing you want to do, obviously, with evaluating a limit is see what the form of the limit is. Is this function we're taking the limit of actually continuous? And we can do that by simply plugging in directly x equal 4 in this case. Notice up top 4 minus 4 is 0, and in the bottom 4 squared is 16 minus 16 is also 0. So this is the form of the limit. I say form of the limit because division by 0 is undefined. So this expression is approaching. And remember, this form is what we call indeterminate. Doesn't mean that the limit doesn't exist. It means we have work to do. And so what's the work? Well, notice we can simplify this expression. In the denominator, I have x squared minus 16. That is a difference of squares. And x squared minus 16 factors as x plus 4 times x minus 4. Notice now we have a common factor of x minus 4 in the numerator and denominator. I can divide numerator and denominator by x minus 4, and I get the following expression. Notice I can now, what's the form of this limit? Well, if I plug in x equal 4, what happens? 4 plus 4, I get 1 over 8, and that indeed is the limit. Couple things in this, I would say. First of all, when we're evaluating the limit, the first thing we want to do is plug in and see the form of the limit. If it's something like if I plug in and I get 2 divided by 3, which is 2/3, that's going to be the limit in the case of the functions we're dealing with. That's what we're going to get, right? There's no work to be done in that case. That means the function's continuous at 4, and the value of the limit is equal to the value of the function. So anytime, though, you get 0 divided by 0, that's indeterminate form. We're going to have to do some work to see if we can find the limit. There's other forms that are determinate. If you get a non-zero number divided by 0, if you remember, we talked about that in the lecture, that's going to give you basically a vertical asymptote, and that's when you have to step back and look at the limit from the right and from the left. When you're showing your support for these problems, this one's real simple, not much to show. Obviously, it's the first one in this section, is going to be real easy. You do want to each time, right? Notice I have these two horizontal lines, one over the other. I hope you know what those things are. Those things are equal signs. And what do you put equal signs between? You put them between things that are equal. And so you should have clearly showing equal signs as you go through this process. I like to do it this way where I keep the limit, and you should have the limit here as well. So when I say use correct limit notation, you make sure you have your limit in front because these two expressions are not equal if this limit sign is not there. Okay, so this original expression is not equal to that. Okay, you need to be clearly showing your work with correct notation. You wouldn't write a sentence without punctuation, without capitalizing the first letter in the sentence, etc., right? You want to show correct work. Notice the limit sign is no longer here. Why is that? Because at that point, we've evaluated this limit. We've plugged in x equal 4, right? This is the value of the function at 4, and it's not indeterminate, so we can go ahead and evaluate it. One other thing, this one's real simple again, but you can also check your work numerically. Don't forget, we've talked about limits first numerically and graphically. Well, I can look, notice I've entered in this function here, and if I go to table set, TBL set, if you remember, I showed you this, put your independent variable into ask mode. So scroll down and just hit enter to highlight that. And then I can go over here to table, and I can plug in values of x close to but not equal to 4, because that's what this means. When we say limit as x approaches 4, we're meaning check values close to but not equal to 4. And we need to see a pattern. So for instance, values less than 4, I plugged in 3.8, 3.9, 3.99. And you can see the values here. Be careful. These are rounded off because the columns are so small. If you push your arrow over and highlight it, you'll see the actual, more decimal places rather for their value. But as we get closer to 4, we can see the values appear to be getting closer and closer, maybe to 0.125, right? Same thing for values greater than 4, 4.2. We have this value, 4.1, that value. and then 4.01, this value. Same thing here. These values are always less than 1.25, but getting closer to it. In fact, it seems like the limit is going to be between, this number here, 0.125156, blah, 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 and this number here, 0.124843, blah, blah, blah. So it must be something in between there. When we see this pattern, right, we know that that limit is close to 0.125. And that's good because 1/8 is 0.125, right? And so this confirms our work. Real quick on number 2, I'll do that one quicker than the last one. I just wanted to go over a few preliminary things. Here's this limit again. We want to plug in x equal -2. If I square -2, I get 4. 6 times -2 is -12. 4 -12 is -8. Adding 8 is 0. Plug in -2 there, I get 0. So it's indeterminate form. So we're going to factor. Now, you should be able to factor x squared plus 6x plus 8 because the coefficient of x squared is 1. We know we're looking for x plus something, where these two things multiply to 8 but add to 6. Obviously, the answer is 2 and 4. But here's another thing. When you plug in -2, right, into a polynomial and you get a 0, you automatically know x minus a -2 or x plus 2 is a factor. You already know this is a factor. And it'll be easier to factor if you realize that. Same thing up here. When I plugged in 4 into this, I got 0. That means what? X minus 4 is a factor. Indeed, it is, right? That's how we factor that. Going back to this one then, the x plus 2's, we now have a common factor. We can divide top and bottom by x plus 2. And notice I just have now the limit as x approaches -2 of x plus 4. Remember, I still have the limit sign here. Notice this limit is determinate. I can now plug in. I get -2 plus 4, which of course is 2, and that's the value of the limit. You could check that numerically. So again, all we're doing here is we're looking at this function, and the limit of this function is the same as the limit of this function because x plus 4 and the original function are the same for all values of x except x equal -2. Obviously, this is undefined at -2, but this is not. If we graph this function here, what would we see? We would see this function, which if you should recognize x plus 4 is just a line, all right? The graph is a line, but there's a hole where in this graph, a hole where at -2 comma 2, right? And so that's what's going on graphically. Okay, so spent a lot of time on this one, but hopefully this makes sense and gets you started on the limits in this section.